Her education background is in the engineering realm. She has a bachelor's and master's degree in electrical engineering from the Universities of Connecticut and Penn State that she parlayed into a PhD in the Department of Natural Resources Management and Engineering at the University of Connecticut. April is also an adjunct professor at Louisiana State University in the School of Plant, Environmental, and Soil Sciences. At the University of South Carolina, April's primary research interests are in microclimate and boundary layer meteorology. Her research involves field measurements and remote sensing techniques with an emphasis on using LiDAR instrumentation for atmospheric applications. And speaking of field measurements, Dr. Hiscox was the PI for the NSF-funded Savant Field Project that took place in 2018 in the wilds of Illinois to quantify the effects of converging shallow cold air drainage and background flow on aerosol transport and dispersion. EOL's ISFS and ISS participated in Savant, which Dr. Hiscox will be talking about in her presentation. We are using Slido to post questions, which you can ask at any time during the seminar. The Slido window is located at the bottom of the presentation screen. Please do not be alarmed if you do not see your question, because we are collecting all questions that will be revealed during the Q&A portion of the talk at the end of the presentation. Dr. April Hiscox, we welcome you to EOL, and the virtual stage is yours.
Okay, thank you very much for that lovely introduction. And thank you very much for inviting me to come talk today. It's really nice to get to talk about some research applications. The last year has been a bit of a change of teaching style, so I have not seen or spoken to as much research as I would normally like. So I'm quite happy to be talking to you about this today. So let's see. Before I get too far underway, I'd like to acknowledge and thank my co-PIs and co-authors on this project, Dr. David Kristovich and Dr. Jinming Wang from the University of Illinois Water Survey, who were my co-PIs for Savant, and a new postdoc that we have working on the project, Sudhir Bimreddy, who is responsible for some of the graphs you will see today. And I also want to acknowledge all the amazing help we had from your EOL folks, Ned Patton, William Brown, Steve Onkley, and a little bit of help from Carmen Napo and Jalen Sun, who have provided some great intellectual conversations as we've worked our way through this. So the title of my talk is Variability in Turbulence Regimes During the Savant Field Campaign. But as we dig into this, you'll see that really it should be called, oh, hang on. I'm on the wrong, there we go. Okay, Variability in Everything During the Savant Field Campaign. So just a few background words on Savant. This was a field project that we did in the fall of 2018 in Illinois, and it was called Stable Atmospheric Variability in Transport. And the motivation for this was that the stable boundary layer is understudied, and particularly from a dispersion perspective. Most of the previous studies have not looked at specifically at triggering mechanisms for different phenomena that can occur in the stable boundary layer, or dispersive effects, or convergence, which I'm going to talk more about. So we really saw that there was both a theoretical need for observations, and we're looking at what happens when shallow drainage converges with background flow. And there was also, at the time we started this, practical considerations. You might have gathered from my background there that I work in the applied realm often. And stability and inversions are, the slide here says recent hot topics in the agricultural spray, operations. Spraying at night, early morning, late evening, or at transition times can often have offsite drift, and there's been a much more renewed interest in this. So we had both these theoretical and practical concerns for our data set. we set out to answer these 4 questions. What conditions, such as cloud cover, threshold wind speed, and stability regime, do these converging flows exist? What scale, spatial and temporal scale of the flows are generated? And do they follow the current theories of wind speed? And then we had a couple of questions about aerosol transport and dispersion. So aerosol, is the aerosol transport and dispersion influenced by turbulence forced oscillations? And what are the effects of intermittent turbulence on drainage? So what I'm going to talk about today, just to give you all some context and scope of the talk today, I'm really going to focus on these first 2 questions. We are digging into the massive data set that is Savant, and I'll give you an overview of the field campaign, and then I'm going to talk about some of the things we've been finding so far. Before that, I've used this term a couple of times, converging flows, and I wanted to clarify that or define it a little bit more specifically. And for the work we're presenting here, or I'm presenting here, define converging flows as flow from cold air drainage merging into an area of relatively slower and less turbulent air. And we think that these flows that there are conditions that can be identified at the mesoscale level of when these converging flows might happen. And we also think that these flows will generate gravity waves or turbulence forced oscillations, which will then in turn affect the dispersion. And then the sub part of that is that long term, the next step is that if we can identify when those conditions will exist, when these flows will set up, that we can identify a relationship between aerosol dispersion and the intensity of the convergence event. So that's the story that we are aiming to tell here. Where we are so far is really digging into the turbulence part of this, these first identification of the convergence flows. So I know many of you, well, actually I don't, because I don't know who's watching the joys of our virtual stage. Where Savant took place in Mahomet, Illinois, which is outside the Urbana-Champaign area. And what we really were interested in was this idea of shallow topography. So we believe, and you'll see in a moment, we were correct, that in this very shallow topography, you can get cold air drainage and there will be converging flows. So the field site was this shallow gully. It had an elevation drop of about 10 meters over just over a kilometer in length, so very small slope. And it was, what its purpose is when it wasn't the Savant field site, is that it's a waterway between corn and soybean crops. So the crops were harvested during the study. Maybe you saw on Jacqueline's background there, she had a photo from Savant when early on, we had mostly corn surrounding the gully. So this area down here was corn, and this was corn, and then a little bit of soybean over here. And the main gully had these 2 feeder gullies, and these are where we believe convergence zones would happen. So ISFS and ISS both came out and set up a ton of instrumentation for us. We had 4 towers along the gully, which ended up with a total of 28 sonic anemometers. We also had temperature and RH probes, net radiation, carbon dioxide, water vapor fluxes, and then an additional 12 small towers that had triangulated pressure sensors and were set up on either side of the main towers to look at cross gully flows. ISS came with the celiometer, SODAR, the RAS system, and a MET station. And then the 3 PIs, each of us has a LiDAR that we are responsible for lack of a better term there, 2 different aerosol LiDARs and 1 Doppler LiDAR, which we ran during Savant as well. We also put out some aerosol point samplers and the C-Temps distributed temperature sensor, which is a fiber optic spatial cable to measure temperature at really high time and space resolution. So the data set is quite extensive, I guess is the right word there. But today I'm just going to talk about some of the results we are seeing from the sonic anemometers, the temperature and RH probes, and the 3 LiDARs themselves. I am very excited to dig into all the rest of this data, but it is going to be probably the rest of my career. So just some pictures to get you a feel for what the towers looked like upon installation. You saw in the previous slide the gully without any vegetation in it. The experiment did cover the pre-harvest and harvest conditions. So we actually ended up with, I like to say, 2 experiments in one, because we've got both a crop covered condition with some channeling effects and then a just straight shallow topography for the second half of it. One of the things we did during the intensive observation periods, the IOPs for Savant, was to go out overnight and release smoke. This is a picture here of the smoke being released, and watch it move down gully or up gully, depending on the conditions. The goal was down gully. So the LiDARs were set up to scan this smoke and watch it for the dispersive questions. Just to further orient you, for those of you not familiar with the Savant campaign, again, here's our gully. We had 4 towers along the main gully, and we named them based on what we hypothesized would be happening there. The first one here, the initiation tower, was at the highest point, not quite the highest point of the gully, but the entrance to the gully where we believed downslope or cold air drainage might initiate. The second tower was the release tower, which is where we were releasing that smoke. And then the 2 convergence towers here, upper convergence and lower convergence, just both at the edge of where feeder gullies were coming in to the main gully. So these are the areas where we thought we would see this converging flow. And just for reference, where we can, what instruments were deployed on each of those towers. You'll see this in the corner of several of the slides just to keep us oriented as we're talking. And again, the slope change between initiation and lower convergence, this is an elevation drop of just like 10 feet. It's a very small elevation drop. Okay, so was very successful. We got a number of IOPs and a lot of data from all of those instruments. And the last 2 years, what we have been doing is really thinking about what it is where to start answering these questions. And we've taken a 3-pronged approach to it. And I'm going to tell you about where we are on all 3 of these things. And there is a common thread through all of them. The first thing that I'm going to talk about, we really dug into, was how to define periods of drainage and or convergence. If we're looking for this time where we have cold air drainage going down the gully and air moving in from one of the feeder gullies and either converging or colliding and possibly triggering other events, we really needed some concrete definition of what this convergence condition was. The second thing we have been focusing on is understanding and integrating the LiDAR images. So I'm going to show you a few results from that. And the third is to look at the turbulence measurements from the towers and compare to the current theories. So we've been doing some comparison with the hockey stick similarity theory. But before I start showing you lots of graphs and data, I want to show you that we really did see drainage and flow. So this is just a video along the gully at one of our later IOPs in early November. And just early morning at the end of an IOP, you can see here, I'm not sure if you're seeing my mouse, but there's a fine layer, a small layer of smoke that was generated from our smoke release all night, moving down the gully, following the gully lines, and then as it moved into the lower convergence area, spreading out and doing some other interesting things. This is the lower convergence tower that you're looking at right here. So yeah, it was successful. So that first question, how to define periods of drainage and or convergence, really narrowing the data set down to when is this happening? When do we have drainage in the main gully and a converging event happening? And what are the thresholds for that to occur? So we've examined several different ways of filtering for convergent conditions, or what I want to call convergent likely conditions at this point. The first is that we believe that a significant change in wind speed near the surface is indicative of drainage. So we looked at the 1.5 meter wind speeds at the lower convergence tower and the release tower. And if there was a change between them, if the wind at the lower convergence tower was faster than the release tower, and the change between them was 10% more than the wind at the initiation tower, we flagged all of those 5-minute periods as convergent likely. Another parameter that we have been considering for identifying this is the wind direction at the upper convergence tower. So looking at wind moving anywhere in a range of 270 degrees from the west, 310 right around here. We've also been examining the LiDAR images to see about plume shape and location changing over time. And then we have not done yet, to look at the aerosol concentration data from the lower convergence and upper convergence towers to see if we have more aerosol data here than more material is moving down the gully. So really focusing on these two areas, the upper convergence and the lower convergence area, where again, we have these two slopes colliding into a slightly flatter region. So I'm going to show you some of the results, what we have so far of applying this significant change in wind speed near the surface. So really taking a look at the entire data set, nighttime data only. We've defined nighttime for our purposes now as 7 p.m. local time to 7 a.m. local time, so the overnight conditions, and going through the entire data set of 5-minute averages to flag periods as convergent likely or not convergent likely. And then looking at that statistically to see if there's something that we can point out as, yes, this is when we're going to have convergent conditions, and this is when we're not going to have convergent conditions. So using this significant change in wind criteria, I've break the data down into 4 different categories here. On the left-hand side, these 2 graphs are conditions pre-harvest, and on the right side are after harvest. We threw out the days where they were actually harvesting. And you can see here, this is, oh, I'm quite sorry, there are no labels on these graphs. Wow. I will tell you what they are. This is wind speed on the x-axis and height above ground in meters on the y-axis. Wow, I would really give my students a hard time for that. So looking at the pre-harvest time period, I'm breaking it down to, these are average wind speeds, average profiles of winds at each tower, all of the conditions that were flagged as convergent likely based on this wind criteria. And these are all of the ones that would be normal or not convergent likely. Periods of time where the wind is too strong, or the gully is not steep enough, or whatever is not allowing drainage to set up in any capacity. So a couple of things, and then the same for post-harvest here. So a couple of things to note is that in the non-likely conditions, we see a bigger change at the higher levels, the above the ground surface, as you move down the tower, with the slowest winds being, or down the gully, with the slowest winds being at the bottom of the gully, and the fastest winds being at the initiation tower. In the convergent likely periods, as you would expect, because this condition sort of dictates that you would identify periods of slower wind speeds. So there's slower wind speeds in the convergent likely periods than the non-likely periods. And we also see a slight difference in the shape of these profiles pre-harvest and post-harvest. Overall, about 31% of the available nighttime data meets this particular cutoff criteria. And of the whole data set, we have 72 nights with data. 51 of them have at least one 5-minute period that would qualify as convergent likely. One thing I'm not showing here is that when we look at the whole data set, flagged for likeliness and not flagged for likeliness, every place experiences slower winds except the lower convergence tower versus normal conditions. So as expected, these convergent conditions only set up in very light wind conditions. So the next step is to start identifying what is that threshold wind speed. We also looked at these two groups of data, the convergent likely and the non-convergent likely, in terms of wind direction, because it's going to be a combination of those two things. So very slow winds, or we thought very slow winds, and wind aligned with the gully direction. So here, looking at the non-convergent likely conditions, and let me explain what you're looking at here, because when you have so many instruments, it's really hard to put them in graphs. So each column here is a tower. So the initiation tower on the left, the release tower, the upper convergence, and then the lower convergence tower on the right. And we are looking bottom up. This is wind direction at the 2.2 meters, so 20 centimeters above the surface, to 1.5 meters above the surface, to 10 meters above the surface. So moving up in height as you move up this graph. And these are wind directions, wind roses for all the normal conditions. And you can see that normal conditions have at the 10-meter height some consistency along the gully. At the 1.5-meter height, there's some impact of the gully in the wind direction. And then at the lowest height, the normal conditions, or the conditions where convergence wouldn't be happening, is primarily when wind is moving this way from release to initiation, except in the convergence zones where wind direction is a little less predictable. Oh, sorry, me go back. Wind moving in the this is the normal conditions, wind moving somewhat up gully at initiation and release, and a little bit more dispersion in the wind direction as we move to the lower parts of the gully. These are the data that's flagged as convergent likely. Again, same conditions at the higher levels, mixed conditions at the lower levels, just 1.5 meters above the ground, and a totally different condition at the upper convergence level, or the upper convergence tower, excuse me. When we break this down, wind directions pre-harvest and post-harvest, we see a difference pre-harvest and post-harvest. This is the entire data set. We see a definite channeling effect of that taller corn on either side of the gully. So for the rest of our analysis, we will always be considering this as two entirely separate scenarios, pre-harvest versus post-harvest. So while the change in wind speed criteria is seems like a very logical way to identify when convergent conditions are happening, we also dug into the data set in a slightly different way to look at some alternate criteria. And what you're looking at here is 2 weeks of data in October from the 16th to the 26th-ish, and several of the different variables at the tower. And what we did through this is to look at particularly the IOPs, where we know we had drainage flow because we were there physically watching the smoke. So we know that we had the conditions that we were trying to identify, and then going back and looking at commonalities during those periods. And all of these are consistent through those periods where the wind speed has to be lower than 2 meters per second, the surface wind speed, the direction aligned along the gully. There's a reduction in friction velocity. So here you can see this is a period highlighted here where we know we had drainage based on the smoke movement. So a reduction in friction velocity to less than 0.1 meters per second. Also a reduction in surface heat flux, a shift in the wind direction profile, which is not shown here, and a drop in the temperature profile, so a dip here. And we just did some comparisons with those different criteria and the other significant speed criteria we were looking at before to see how much of the data set would break into these different categories. Of the 75 days available, well, 72, ignoring the 3 for harvest, less of the data set is flagged if you use wind direction, and even less of the data set would be flagged if we use the temperature component. So right now we are looking at ways to combine some of these to really more concretely identify convergence. The second thing we have been looking at is the LiDAR images, which I suspect is maybe the most interesting. This is the one of the unique things about Savant was having all 3 of these LiDARs deployed at the same time and in combination. So just some words about the 3 LiDARs. The 2 on the left there are, we call them mostly aerosol LiDARs, but one does has a Raman channel. They are very similar in their functionality, although the University of Illinois model is slightly newer and upgraded to the USC LiDAR. It has a better range resolution. We took range height indicator scans with both of those. I'll show you on the map on the next slide. And then we also had the Halo Photonics Doppler LiDAR that has an 18-meter range resolution, taking volumetric scans during the IOPs. So this is the configuration for the LiDARs, how they were actually deployed. These are the dates of the IOPs, but the Doppler LiDAR was positioned at the bottom of the gully, even further down the gully than the lower convergence tower, and scanned the entire region in volumetric scans. The two Aerosol LiDARs, one was positioned right next to the release tower. So it was scanning, the goal was for it to be scanning along the length of the plume. And the other was positioned at the top of feeder gully 2, and it was set to scan the cross plume. So we wanted the highest resolution in the cross plume spread here. So there is a point here where we have two LiDAR scans crossing each other, two Aerosol LiDAR scans crossing each other, and the Doppler scanning the whole thing. Rather than you looking at my hands trying to explain that, let me show it to you in data. So we see here, these are scans from all three LiDARs at the same time. The USC Aerosol LiDAR looking along the plume, so along here. In this cartoon, imagine the smoke moving all the way down here. This LiDAR scan is the cross of it. So this crosses here. And then the Doppler LiDAR looking across the whole field. And the Doppler LiDAR being able to identify periods of time when we have flow towards the LiDAR and flow away from the LiDAR. What we've seen so far in the LiDAR data is not super surprising, but also more confirmation between that there is a pretty drastic difference between pre-harvest and post-harvest. We saw much deeper and narrower drainage flows during the pre-harvest IOPs, and post-harvest drainage flows were shallower and broader, and sometimes spreading out across the gully, and as it reached down into the lower convergence zone, just spreading entirely as the faster moving air from the gullies converged with the not moving air at the bottom of the gully. So digging into the LiDAR data a little bit and trying to, again, identify, we've got what periods of time are convergent likely, what is the trigger for the onset of that flow. So what you're looking at here is LiDAR backscatter, height above the ground. This is all from the Doppler LiDAR with height above the ground on the y-axis. And each of these panels is approximately 30 minutes apart, 10 minutes apart, sorry. So pre the onset of gully flow, we see, and the three lines are further away from the LiDAR. The background backscatter has the same throughout, and then we see this increase in backscatter near the surface. And we also see a shift in background intensity and radial velocity. So we are looking at these images to identify how deep the flow was during these periods of time that we are interested in. And you can see a similar pattern from the background winds from the LiDAR. So this is flow towards the LiDAR and away from the LiDAR. And we see this acceleration flow towards the LiDAR during this particular IOP. Yeah, I have just about 10 minutes left. So I'm just going to go through these slides slightly quickly here. When we look at all the IOPs and classify the LiDAR data in this way, we have identified 3 different types of flows from the IOPs. The first being where we see an increase in the depth of down gully flow, which we believe due to opposing winds near the surface. So winds coming from multiple directions. We also see periods of time where there is a slightly elevated down gully flow during opposing background winds again. And Here we also see a different type of flow that's a more dispersive drainage flow that spreads the plume very far across the gully and down into this sort of, I'm not really sure what the right word is there. Okay, so the last thing that we have been looking at is comparing this turbulence data to current theories. So really, again, taking this meta view of the whole nocturnal data set, 7 p.m. to 7 a.m. To look at stability and turbulence in this set. Looking here, just a sort of percentage pie charts of how changes in stability were pre-harvest and post-harvest. So in all cases, except the lower convergence tower, there was a increase in stable conditions post-harvest, which, so there's just more data to look at post-harvest. And this is just a simple classification of stability based on a temperature difference. But we see variations in each night. So here we have one night, October 18th, which you saw in some of the previous graphs as well. This is the night we've really dug into. It was one of the better IOPs. This is half hours across the evening in the bottom, potential temperature, and in the top, wind speed. And as we go from dark blue to yellow, dark blue is just after sunset, yellow just before sunrise. So as we go later into the night, moving from more stable to neutral and a decrease in wind speed. And then this is a second night where we see the same transition in the stability or the temperature profiles, the cooling and the straightening of the profile, but very different conditions, still very low wind speed conditions, but a lot more variable as you move away from the surface. We've done some similarity relations tests, pre-harvest, post-harvest colored here, and it's following similarity theory, so that's good. What we do see is when we look at a drainage flow night versus a normal night, drainage flow does not follow the similarity theory in the way that it should. So these are all periods of time, and we have a number of these periods of time that do not follow the current, the Mononobekoff similarity theory, which we are now looking at the hockey stick transition analysis. For those of you not familiar, this is comes from Jay Lund's work, where she has proposed these 3 different turbulent regimes during nocturnal conditions. And what it's saying is that as wind speed increases, turbulence intensity increases, but that it increases in 3 different ways. That it increases linearly above a threshold wind speed, and not as steeply, that there's 2 different slopes, which the intensity increases with wind speed. And then she also identifies this 3rd regime of transition. So moving between these 3 regimes. And looking at this, I don't know if this is good news or bad news, but good news is we have examples of all 3 regimes, and I'm going to show you those now. So in regime 1, where turbulence intensity increases gradually with wind speed, these are the these dotted lines are the data from cases 99, which Jalen used to identify the threshold wind speed and propose some of this theory. So this is one example of a night where we see throughout the entire night at all heights, everything being in regime 1, where the intensity increases very gradually with wind speed. We have other nights that look more like this, where we see turbulence intensity increasing linearly with wind speed at a pretty strong slope. And we have other nights, all three of these graphs are from the lower convergence tower, other nights where we see higher turbulence intensity even at lower wind speeds throughout the entire night. So we have examples of long periods of time with all 3 regimes staying with all 3 regimes. Oops. And we have other nights that have the full-on hockey stick with increasing, where we will be able to identify this threshold wind speed, all of the regimes in one night. So you see that there. Okay, so in summary, sorry, I was watching the time there and I sped up a little bit at the end. So please ask questions I would really like to discuss more. We've tested the similarity relations before and after harvesting the crop, and the crop definitely impacts the drainage. When we compare with the hockey stick turbulent regimes, we see all the regimes in the data set. So far, digging in, what we're looking at now is comparing those flagged conditions that we consider convergent likely with what turbulence regime we see. Mostly we see regime 1 and 2 during the convergent likely periods. We can see downslope drainage flow with all 3 lidars. The pre-harvest flows are narrower and deeper. We see an increase in drainage flow depth when there are winds moving both down and up gully. And right now, from what we've looked at so far, in really low wind conditions, the wind direction doesn't seem to play a role in drainage potential. So when the wind drainage will exist when the wind is low enough, it doesn't matter what direction the wind is coming from. And what we have not yet quantified, but see in different ways, is that drainage itself can be intermittent. We have several nights where 5-minute period to 5-minute period, it flags as likely, not likely, likely for 10 minutes, not likely, where there's some intermittency in these filters, I guess, for lack of a better word right now. So that's where we're looking right now. With that, I think I'm right on time for 15 minutes of questions. I would really love to thank EOL. This was a big, difficult project. We encountered quite a few challenges in getting all these instruments up, but they were all up and worked. We have a very rich data set. I'd like to thank Ken Dollenberg from Scattered Acre Farms, who kindly allowed us to set up all of these towers and everything on his private property, on his working farm, and the Lake of the Woods Preserve, who also allowed some tower stuff. And you can see all of the rest of the acknowledgements there. And with that, I will take questions. Okay.
Great. Well, thank you, Dr. Hiscox, for a wonderful presentation. It's very nice to see EOL data and some very cool LiDAR analysis. So
there is so much data. I'm like, we're just so excited.
That's what we do. So we have plenty of time for questions. Again, please use the Slido interface, which is below the presentation screen if you scroll down. And while we're waiting for questions, I have a question, not being a boundary layer meteorologist, but why is the pre and the post-harvest convergence different? I mean, I could guess it has something to do with the fact that there are tall plants, but maybe you can elaborate.
It is exactly that those plants are tall. The corn was tall enough and dense enough to form a channeling and sort of enhance the valley effect, right? So it pushes it all downslope rather than allowing some of the, yes, we have considered, oh, sorry.
So we have a question from Sean. Have you considered classifying the flow turbulence regimes using the bulk Richardson number?
Yes, bulk Richardson number is on our list of things to look at. And actually, I sort of glossed over it there at the end, but the images on the right for those different regimes were Richardson number versus variance in TKE. So that is definitely on our list of things to do.
Thank you.
I don't know if I have much more to say about that, but
it's a TBD, right? We have another question from Amy Mills from the University of Southern Maine. Thank you for a great presentation. What kinds of new research directions do you see this project opening for you over the long term?
Well, that's also a great question. There's a ton to be done here. As I said, we're just looking at really getting a handle on this data set. And every time we meet and talk about what we've been doing, we come up with a number of other questions of well, what if we had more data that looked like this? And what are those conditions? So I think we often joke that Savant 2 is in our long-term future. But I think I need a few more years of recovering from a big field project before that. And then really turning this into some more applied recommendations. One of the students who was on the project with us is writing a thesis based on like an inversion climatology that will be hopefully usable to I'm forgetting, but in Illinois, there is a network of inversion prediction for folks to know when to spray, and so maybe bettering that a little bit. I don't know. Lots of fun stuff.
Great question for the future. Thank you.
Thanks.
And we have a question from Steve Onkley.
Oh, Steve. Hi, Steve. That is an excellent question, and I'm going to go with probably. We've just hired a student who started just this last week, and he's been digging into the CTEMS data. We met this morning, and there is some useful data there. I know during the campaign, I said that instrument was a big pain, and that I would withhold my judgment as to whether or not it was a useful instrument until I saw the real data. And jury's still out, but it's looking positive. Say that. He's working on calibrating it and identifying stuff. So yes.
So for those who are calling in and don't have video, the question was whether there was usable CTEMPS data from Steve. Thanks, Steve. We have a question from Jürgen, who's at RAF. The smoke looks to have a considerable optical depth. Without the smoke, the main cooling is at the surface. With smoke, there may be more cooling at the top of the smoke. Does the smoke thus change the flow characteristics?
I don't believe so. We've used smoke like this in the past. We cool it. I don't know, you probably couldn't see in the pictures there, but smoke is maybe not the best word for it. It's more akin to a tracer. It's generated by a smoke machine, but it's neutrally buoyant when it comes out. when we actually release it. So it's cooled to be the same temperature as the background flow. So I don't think it changes the flow characteristics. It's a really great question. I'm trying to think how we could expand on that a little bit more, but I don't think so.
Thanks, Jürgen.
Thanks, Jürgen.
So just to follow on Savant 2 and my first question about the difference between pre and post harvest conversion. So if you did these measurements over terrain with very little vegetation, would you see a dispersed flow pattern similar to a post harvest analysis? Would you expect to see something like that?
Yes, I would. I think that this shallow topography, there's a lot more in there than we really give it credit for. It's not flat at all. There are noticeable differences just over this small distance. So without just in the plains, you would see dispersive effects like this if you had something that was released strong enough. Yeah.
Right.
That answer your question?
We have a question from your colleague, from our very own Cubed, Ed Patton, and he asks, did the drainage flow ever exceed the height of the corn during drainage nights?
Ooh. I haven't looked at it. I don't know off the top of my head. I'm going to write that down and get back to you on that one then. Because heights of corn. I don't know. I haven't looked at it quite that closely. Sorry.
Thanks, Ed. We still have time for more questions. Did you have to worry about interference from the plants on the sensors at the lowest levels? Were there incidents of interruption, plants growing and interfering with the measurements?
No, not really. We kept all of the instruments were in the main gully, so there was not any. It was just grass there. Some of it grew a little bit, but not enough over the course of the period. We started in September and went into November, so it was the time where things were starting to die. So we actually had the opposite, that at the end of it, we had snow underneath some of the sensors rather than grass.
Okay. Thanks, April. We have a question from Matt Paulus, who's at ISF. Are there any additional measurements you wish you had now that you've looked at in the data in depth?
Yeah, so one thing we did was on a couple of the towers, we had the temperature and the sonics split. So we have, I can't remember exactly right now, but we have like temperature at 8.5 and the sonics at 10 or vice versa, which I know is just like a practical consideration, but I kind of wish that they were at the same point. And I kind of wish that we had all 4 towers go all the way to 20 meters, which those of you who know the whole story know why that is, but there's a couple of times where I want to see that higher measurement on I kind of feel like I know what's happening up there, but I want it.
We'll just put that on our wish list. We all have wish lists, right, when we set up field campaigns.
Yep. Yeah.
But it's good to know.
This was this was a great project. We had a lot of fun. We had worked hard. You guys worked really hard. EOL worked really hard for us, and we are super appreciative of it.
Well, we have another question coming up. from Gary Granger, who is also at ISF, and you might know from Savant. But Gary asks, how much does river flow and convergence relate to the study of drainage convergence?
They're kind of the same processes. I mean, you mean like a regular river, not an atmospheric river, I'm assuming. The different densities are going to change it, but I think the same processes are going to happen where this convergence is occurring. I don't know. And this is a very weird format.
Thanks, April. We have a question from Jeff Weil. Does the drainage flow depth depend on time through the night? And if so, maybe with the time integrated height flux akin to Ted Yamada's model for stable boundary layer temperature profile?
The depth, how to answer this? The depth increases after onset, but the onset doesn't necessarily, but it can like onset and get deeper and then break down and then onset and get deeper again. So yes and no. I feel like I'm really doing a bad job answering these questions. So it does increase once it starts, but it doesn't increase continuously throughout the night, and the time that it starts is dependent on something else, and that's really what we're trying to identify now. Yeah.
Great. Well, I don't see any questions coming up. We've had a really lovely number of questions come up already. Thank you, April, for answering them. And thanks for asking your interest in giving a seminar at EOL.
Yeah, thank you for having me.
So if you are interested in this research and have further questions, please reach out to April via her email, which is on the seminar flyer. On behalf of EOL, I would like to thank Dr. April Hiscox for giving us the opportunity to hear about her boundary layer work incorporating ISFS and ISS Savant data. We love seeing our data used wisely and creatively. So thank you, everyone, and have a great day.
Thank you.